Hi everyone, I am Harsh. I'm presenting our work on domain adaptation via context prediction for engineering diagram search. This is joint work with my advisor, Taylor Kirkpatrick. Engineering assembly diagrams are used to show how different parts of a product assembly fit with each other. The retrieval task at hand is to retrieve most relevant assembly diagram images corresponding to a part or a sub-assembly query image. For example, for the two query images shown on the bottom right, aim is for a system to retrieve the assembly diagram B. Prior works in this task have relied mostly on pre-trained deep neural networks for image feature extraction, such as VGGNet pre-trained on ImageNet photographs. But diagram images have certain different properties. We believe search may benefit from feature representations that better account for the structure, which is very important for such assembly diagrams. In this work, we propose to use spatial context prediction to learn assembly diagram feature representation. We believe that this can better encode the structural properties of the diagram images. To understand the idea behind context prediction, consider a diagram image I and a patch A drawn from that image. Now let's consider three more patches from the same image, B1, B2, B3. Which among these is more likely to be just beneath the image patch A? Well, if we observe that how the vertical bar type component in patch B1 aligns nicely with the patch A, we would conclude that having B1 beneath patch A leads to a more overall consistent assembly diagram as opposed to the other two choices. In this work, we develop a system which incorporates such spatial context into the image features. Such idea of context prediction has been tried before. For example, Deutsch et al. Used it for learning visual representations from scratch for a different domain. In this work, we adapt the spatial context prediction idea for use in diagram search. However, using only context prediction to train feature extractor from scratch does not provide good results, uh, probably because of the smaller size of the engineering diagram datasets. As such, we want to leverage pre-trained networks also, which have been shown to learn abstract features like lines and shapes. Therefore, we propose spaces, a method to fine-tune pre-trained image feature extractors using context prediction. Next, I will describe the proposed approach. Consider an image I. We randomly pick a rectangular patch A of size m cross m. Thereafter, we choose one of the 8 cardinal directions, which we denote as D, uniformly at random. Then a second rectangular patch B is identified in the vicinity of A in the direction D from A. We realize the context prediction idea through the 8-way classifier, which takes as input the extracted features of the ordered image pair A, B. Here, theta represents the classifier parameters, phi represents the image feature extractor parameters, and Fi represents the extracted features themselves. The resulting loss term S, which we refer to as spatial loss term, jointly updates both phi and theta parameters through backpropagation. Note that there can be a very large number of such image patch pairs. As such, we only sample certain number of patch pairs across the images in the dataset. Next, as motivated earlier, pre-trained models do provide certain useful features. Therefore, we encourage the model to stay close to the original pre-trained parameters phi naught via a L1 penalty loss. Thus, our final loss L has two terms, the spatial context loss, and the L1 penalty loss. We experiment with IKEA dataset, which consists of around 17,000 furniture assembly diagrams. The query images in this dataset were generated automatically. The dataset consists of 5 query types. The lowercase letters signify that position, scale, and rotation respectively are unchanged, while the corresponding capital letters denote the corresponding altered attribute. We use retrieval methods used in the prior work. We consider following baselines. VGG is a fixed pre-trained model used in prior work. CTXT is using context prediction to train feature extractor from scratch, while VGG-AE uses auto-encoding objective instead of context prediction to fine-tune the pre-trained model. The proposed method spaces performs much better than all the baselines across all the different query types, especially the toughest query set, which is capital P, capital S, capital R, on the top right, uh, demonstrates largest relative gains in spaces. Our paper has more detailed results and analysis. So to conclude, we propose a new method for unsupervised adaptation of out-of-domain feature extractor that asks the model to reason about spatial context. Standard unsupervised techniques such as using auto-encoding objective leads to burst performance. And finally, our proposed method leads to substantial improvements on a downstream search task, yielding state-of-the-art results on the IKEA dataset.